All right, like I said, we actually doing a continuation of where we left. So remember, Euclidean geometry is application for both grade 11 and grade 12. So what I did last time when we met is I did some of the sub basics that we supposed to familiarize ourselves with. We spoke about the triangles, and this is what we have learned, I think, in previous grades such as grade 10, grade 9, and so forth. We spoke about the triangles, types of triangles, scalene, isosceles, equilateral triangles, right angle triangles. And we also spoke about the relationship between the angles, right? How to determine the angles inside of a triangle. We know all of these things. We all know all of these things. And then we also spoke about the congruency. And I said that the two triangles, if they are congruent, that means they have equal sides, they have equal angles, they are exactly the same. That's the congruency. And we have learned the rules on how to prove congruency. And therefore, we also spoke about the similarity. I said two triangles, for them to be similar. What does that mean? That means they are equiangular. That means they have equal angles. So if two triangles are similar, that does not mean they have equal laterals. Remember, what did I say? What are laterals? The laterals are also called the sides. So we have two triangles over here, which is ABC, and then we have triangle DEF. We spoke about the similarity, that they have same angles, but the sides are not the same. That's similarity. They are in the same proportion. The ratio is the same. And I said to you, I did emphasis under similarity. I said the similarity is more applicable here in grade 12. Okay, we're gonna deal much of similarity here in grade 12. And therefore we spoke about the theorem of Pythagoras. We all know this. And then I showed you how to prove this, right? Using similarity. If two triangles are equiangular, last time I showed you how to prove this. Like I said, this is for grade 12. Okay, this is for grade 12. And therefore, these are the properties of quadrilaterals, and you need to know these properties, whether you're in grade 10, whether you're in grade 11, whether you're in grade 12. We also discussed the properties of quadrilaterals, right? Remember, what are quadrilaterals? Are four-sided shapes or four-sided figures. So quad means four, lateral means side, meaning we are talking about four-sided shapes such as trapezium, rectangle, rhombus, parallelogram. These are the properties that we already discussed. Square and the kite, we also spoke about this. Again, how to prove that this figure, it is quadrilateral. These are the methods. We also went through this, okay? Now, this is where I supposed to start with you. So we're supposed to start here where we are actually going to talk about the circle geometry. This circle geometry, it's a basic from grade 11. If you really struggle with Euclidean geometry, that means you don't understand this portion from grade 11. So grade 11s, you guys are going to benefit. The grade 12s, make sure that you grasp the information. And let us start with circle geometry. So now what is presented over here is a circle, right? We have a circle presented over here. Let me see. I think we actually have a, let me see. We have someone who is struggling. Let me tell her to join using the audio. She's supposed to use the audio. Let me text her right now. Let me text her right now. All right. All right. All right. Let me do this. My recording. All right. So now the key definitions, like I said, you need to familiarize yourselves with these terminologies, because if you don't understand them, remember, we are going to talk about the theorems. So now, how are you going to understand the theorems without understanding the terminologies? So it is very important. You're just given a simple cycle, right? In this cycle, They are lines, but you need to understand these lines as mathematicians. Let me tell you this, you're still gonna learn more about these lines when you get at the university. It doesn't only end at grade 11 or grade 12. So now let's talk about this circle. Now, the circle provided to us, we have a line that touches the circle only at one point. Look at this point. We have a line that touches the circle only at one point. What do you call that line? We call it a tangent. So the reason why you need to learn these terminologies is because you're not supposed to confuse these terminologies, and you're supposed to understand that when you are given a tangent, what are you actually given, and how are you going to apply that to solve different questions? Okay, that's very important. And therefore, again, we still do have a circle, but look at this line. What is happening with this line? It is a little bit different from the tangent because it is now inside of the circle. And this line, it touches our circle at 2 points. What do we call the points of the circle? We call them the circumference. So that means this line, which is called the secant, it touches the circumference at 2 points. And be careful, this line, it is also going outside of the circle. And therefore, what do we call this line? It is called the secant. Okay? And therefore, we have a line that is called diameter, and I believe all of you understand this line. But be careful. A diameter, it is a line that passes through a center. If a circle does not have a center, or if you were not told that this circle has a center, remember, in Euclidean geometry, you do not assume unless if you are told, or unless if you have proven it, okay? So something might look like a diameter, but if you're not told that it is a diameter, it is not a diameter. If you are not told that this line is a diameter, or if you're not told that we have a center, that means this line is not a diameter. So a diameter, it is a line that always passes through the center of the circle. Okay? It's a diameter. So now, what's the difference between the diameter and the secant? The secant, it is a line that touches circumference to circumference. A diameter, it is a line also that touches circumference to circumference. But the difference is secant, it doesn't pass through the center. Number two, secant, it goes outside of the circle. You see why you need to know these terms. And therefore, we have what you call the radius. Radius, it is always a line that comes from the center to the circumference of the circle. That's a radius, okay? So now when you have two radii, like for example, we can see that from this center to that circumference, again, from this center to that circumference, we have two radii, right? Now, these two radii, they form a sector. So meaning this portion that looks like a pizza, it is called a sector. You will understand these things much more better when we do the applications while we are proving the theorems. Angle subtended by a sector, blah, 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 blah. By now, you know what is a sector when we say angle subtended by a sector. That's the reason why we need to learn these things, okay? And therefore, we have a chord. We have what you call a chord. Now, what is a chord? A chord, it is a line that touches circumference to circumference of the circle. But be careful, the chord, it is different from the secant. How? The chord doesn't go outside of the circle, but the secant, it goes outside of the circle. And look at the chord. The chord, it is also different from the diameter. How? I understand that a diameter, it is inside of the circle, circumference to circumference inside of the circle. Same applies to the chord. It is inside of the circle, circumference to circumference. But look at the diameter. Diameter passes through the center, but the chord, it is not passing through the center. So be able to distinguish all of these lines, okay? And therefore, we have what you call the segment. So now the segment is going to be between the chord and the arc. So that means this is an arc, okay? This is an arc, which is this portion over here, this smiley portion over here. From this point to that point, we have an arc, and therefore we have the chord. So the portion that we find between the chord and the arc, it is called a segment. Hence why when we talk about the theorems, they will say angle subtended by the chord, or angle subtended by the segment, or angles in the same segment, or now you will know what are the segments. Okay, so these are key definitions that you need to understand before continuing with this topic, which is called the circle geometry. Now, having a look at these terminologies, you can read through them. Okay, they're still fine. You learn through them. This is what I've just already explained. And therefore, we have the chord. Look at the chord, circumference to circumference. And then we have, look at the dotted lines. These dotted lines, let me try to zoom over here. Look at the dotted lines over here. The dotted lines over here, what do we have? We have the arc, but this is the major arc, and this is the minor arc, the solid ones. It's a minor arc, and therefore we have the sector. Remember, what is the sector? It is our pizza, right? And therefore here we have the segment. Look at the segment. This is our segment. Remember, the segment, it is between the chord and the arc. That's our segment. And then here we have the diameter again, line from center to circumference, from circumference to center. We have the diameter, and then here we have the radius. And then look at this circle over here. We have half of a circle. So if you have a line that passes through the center, what is the line that passes through the center? Remember, it is a diameter, right? So if you have a diameter over here, we have what you call the semicircle, okay? So here we have the semicircle. This portion over here, it is not the segment. It is semicircle. Don't confuse the segment and semicircle. You see over here, between this chord and this arc, we have the segment. But between the diameter and the arc, we have the semicircle, not the segment. And then we have the tangent. Remember, the tangent, it is a line that touches your circle only at one point. Secant, it's like a tangent. Look, secant is like a tangent, but the problem about the secant is secant, it touches our circle at 2 points, but the tangent, it touches our circle only at 1 point. So be careful about that, okay? This is just a quick reminder on how these things actually works. All right, I hope that was clear. Remember, if you have the question, make sure that you open up your mic and you ask me where you really do not understand. I'll be open and willing to take your questions. Now, this is the revision of grade 11. Like I said, the theorems, this is what we have learned in grade 11, right? We have learned numerous Euclidean geometry theorems. The first theorem that we have learned, it is this one, which is denoted by this big circle over here. But the question is, how do we read the theorem? Here, I am not proving it yet. I'll show you how to prove it, but not now, okay? We have the theorem which says, or which state that this theorem states that, this is theorem number 1, right? It states that the line segment joining the center of a circle to the midpoint of chord is perpendicular to chord. What does this theorem say? It says this. Let me change. Let me go to my pen. You have a circle. You have the center of the circle, which center O, and then you have a line that is from the center to this line, which is called AB. What do we call this line, which you call the AB? We have just learned the terminology not so long ago. We said the line AB, it is called the chord, right? So if you have a line from center, and this line from center, be careful, it doesn't touch the circumference. So this line, it is not radius. So what is the name of this line? It is called OM. Can you see the line OM? Line OM. If it touches line AB at the point M, what does that mean? It is this theorem. The line segment joining the center of a circle to the midpoint of a chord. Midpoint of a chord is perpendicular to the chord. So that means this line, which is called line OM, it will act perpendicular to line AB. Why? Because this line from center, it touches chord AM, whereby chord AM, it is divided into 2 equal sections. I'll try to show you what do I mean by saying that. Now, let's have a look at this point over here. They say to us, if you have a circle, right? And then you have the center, and therefore you have the chord. We will call this chord A, B. And therefore, let's say this line from center to the chord, and this line from center to the chord, it happens that, let's call this line OM, right? This line, we will call it line OM from the center. So if it happens that this line, which is line OM, it cuts AM, which is from there to there, to be equals to MB, which is from there to there. If it happens that AM is equals to MB, I agree we have this line from the center and it cuts the chords. And it happens that the way this line cuts these chords, it happens that AM will be equals to MB when this line cuts, when line OM cuts AB. So according to this theorem, if this is the case, what does that mean? That means if this is the case, that means OM will be perpendicular to AB. If this is the case, then this is the scenario. Okay? If line from center cuts chord AB into two equal parts, that means OM will act perpendicular to AB. This theorem states that, and it's what you're supposed to know. So you knowing this theorem, you will be able to apply it when solving different questions. But you will see how. You just need to understand the theorem, how it unfolds. Okay? So that means if OM is perpendicular to AB, that means this angle over here, I'll call this angle M1, and then I'll call this angle M2. So that means angle M1 will be equals to 90 degrees, so as angle M2, if this is the case. What is going to be provided in exam? Maybe if you want to spot out this theorem, you'll be provided with the blue color. You'll be provided only with the circle, center, and line OM and AB, and they tell you that AM is equals to MB. So the answer to this is that M1 and M2 is 90 degrees. Why? Because it's theorem number 1. It states so. Now, each and every theorem, it has the converse. But now, what is the converse? The converse, it is the reverse of the theorem. You are given AM is equals to MB, then OM is perpendicular to AB. But if you are given that OM is perpendicular, let me write it here so that it can make sense to you. Now, the converse of this theorem, it states that, let's say you are given the circle, and then you have the center, you have the chord, and then you have the line that is coming from center to the chord. Let's call this chord AB. Let's call this center O. And therefore, from this point to that point, we have point M. Therefore, this line, we will call it line M. I mean, line OM, okay? Look, the theorem and the converse are different, but they do the same thing. Né? So what is provided here is, this is exam, right? You're going to be given this, and you're going to be told that OM is actually perpendicular to AB. That means here we have 90 degrees, right? So this is the converse of theorem number 1. How does the converse work? Remember, you are given this. Ne? This is all given. This is all given. You are given the diagram, and you are given that OM is perpendicular to AB. So what is the answer to this? The answer to this is, if OM is perpendicular to AB, what does that mean? That means side AM will actually be equals to side MB. That means this side will be equals to that side. That's the converse of the theorem. It is a reverse of the theorem. But actually, what does the theorem say? The theorem says if you are given the circle, center, chord, line from center, let's call this A, B, O, and M. Here, this is the theorem. What are you going to be given? You are going to be given that AB is equals to, sorry, AM, yes, M. AM is equals to MB. Remember that it's B. AM is equals to MB. So what does that mean? If you are given that AM is equals to MB, that means OM is perpendicular to AB. That means here is 90 degrees. If you are given this side is equals to that side, that means there it's 90 degrees. You see, it does the same thing. It's just that the other one is the theorem and the other one, it is the converse. Converse, it is the reverse of the theorem. Okay, but we'll learn how to prove these things at first. That's the theorem number one. Always know how theorem number one works. It works like that. That's what you need to know. That's what you need to understand. Now we move to theorem number two. Now, how does the theorem number two works? There are three of them, okay? But they do the same thing except this one. But I'll show you except this one when we prove, not now, okay? So now, what does the theorem number two state? Remember, this is theorem number one, and this will be theorem number two. So what does the theorem number two state? Theorem number two states that the angle which an arc of a circle subtend at the center of the circle is twice the angle it subtends at the circumference of the circle. So to simplify this long statement, you'll read it to understand it after me explaining this. Ne? Theorem number two, it says to us, the angle at center is twice the angle at circumference. So let me draw the circle again. We have the circle, right? I'm going to draw this shape, which is shape ABC. Remember, we have the center. Here's the center of the circle. And therefore, we have our center. It will be called center O, right? And therefore, we're going to have OA, which is this side over here. It's radius. We're going to have OB, which is this side over here. It is also the radius. And then we're going to have AC, A to C. Here we have C. And then we're going to have CB again. We have, these are the chords. Look at them. They are the chords, right? We have chord CB. Now, this theorem, which is theorem number two, it says that angle at center, where's the angle at center? This is the angle at center. Let me change my color. This is the angle at center, right? What is the name of that angle at center? It's called the A angle OB. This angle at center, it's called A angle OB. So this theorem says that angle at center is twice which angle? Angle at center is 2 times angle at circumference. Angle at circum for circumference, okay? It states that angle at center is twice angle at the circumference. But where is the angle at the circumference? This is the angle at the circumference. This angle over there. So what is the name of the angle at the circumference? It is angle ACB. So meaning it's A angle CB. This theorem states this. Right? Angle at center is twice angle at the circumference. So that means practically, if this angle over here, it's let's say it's 20 degrees. 20 degrees. Let me say 60 degrees. If this angle over here, it's 60 degrees, which is the angle at center, what will be the angle at the circumference? It's going to be 30 degrees. The angle circumference is going to be 30 degrees. Because angle at center is 2 times angle at circumference. So when you take angle at circumference and then you multiply it by 2, remember what is the angle at circumference? Is 30 degrees. You're going to get 60 degrees. So that means angle at center, which is 60 degrees, is going to be 2 times angle at the circumference. The angle at the circumference is 30 degrees, and therefore 60 degrees will be equals to 2 multiplied by 30. It will be 60 degrees. So this is what this theorem actually states. It states that the angle at center is twice the angle at the circumference. So based on these based on these 3 diagrams, they explain exact same thing. It's just that the diagrams are not the same. In this diagram, you just only locate the angle at the center. So in this case, what is the angle at the center? The angle at the center, it is this one over here, which is called AOB. So that means here, A angle OB is going to be twice which angle at the circumference? It's going to be twice this angle, which is at the circumference. Okay? Which is at the circumference. In that case, it will be angle C. So that means if this angle is 60 degrees, which is AOB, that angle at center, that angle at the circumference, it will be 30 degrees. You can also say the angle at circumference is half the angle at center, or you can say the angle at center is twice the angle at the circumference. Okay, that's how you can say the theorem. But I want you to be careful. Why do we say the angle at center is twice the angle at circumference? It's because these two angles, look at the angle at the center. Remember, let me go to my diagram. The angle at the center is this one, right? And the angle at the circumference is that one, which I said is 30 degrees. Now, having a look at these two angles are actually subtended by the same arc. But what is the name of the arc? Here's the arc AB. Ne? So these angles, for us to say angle at center is twice angle at the circumference, we saying this because these two angles are subtended by the same arc. These angles, they're supposed to be subtended by the same arc. That's why when we read here, they say to us, the angle which an arc of a circle subtends at the center of the circle is twice the angle it subtends at the circumference of the circle. We're supposed to have the arc there. This arc, which is arc AB, is subtend at this angle. At the very same time, it subtends that angle over there. So the angle, it is subtended by the same arc. Look at this diagram again. We have arc AB once more again. It subtends this angle at the center. It also, look, it also subtends. It also faces the angle at the circumference over there. Even this diagram, this is the angle at center. We have the angle at center. It's twice angle at the circumference. But look at this angle at center. It is subtended by this arc, this big arc, which is arc AB. It subtends this angle at the center. It also subtends that angle at the circumference. So you see, this angle is at the circumference, but I want you to note this angle also, it is at the circumference, this angle. It is also the angle at the circumference. But you see, it is subtended by this arc now. It is subtended by arc AC. So it is not the same arc. So we need to have the same arc subtending angle at the center, at the same time subtending angle at the circumference to say, to state theorem number 2.